Hello and welcome you all to the 20th lecture of this NPTEL course called Electroweak Interactions in the Standard Model of Particle Physics. Now, in the last lecture, what we did that we basically imposed the quantization conditions on the scalar fields. So, I mean, which is the Klein-Gordon Lagrangian, and upon that imposition of quantization conditions, which is via step 1 to write the Hamiltonian, step 2 by imposing the commutation relation between the fields and its conjugate momenta, then third by the mode expansion using creation and annihilation operators, and then showing that finally the Hamiltonian can be written in terms of the quantized energy of particles. We finally interpret that those scalar fields with which we started writing the Lagrangian and then the Hamiltonian now has the interpretation of quantum scalar particles, right? So, this was basically the introduction that we actually had. Now, today we are going to carry this same exercise forward for the case of fermions and for the electromagnetic fields. Now, for both of these cases, we actually have introduced the basic Lagrangian, and now we have to see how we can impose the quantization condition. So, now they get elevated not just as Dirac fields, but as electrons, as particles, okay, or not just in terms of electromagnetic field, but in terms of photon. So, I am going to take you through those two cases in today's lecture. So, let us get started with the first thing that I am going to first talk about the Dirac field. Now, you all recall that we wrote the Dirac equation and the Dirac Lagrangian consequently, and the Dirac Lagrangian was what? It was actually psi bar I gamma mu del mu minus m psi. Right? And what was the gamma mu? Gamma mu are called the Dirac matrices, del mu is the fourth derivative, and what was psi bar? Psi bar is the conjugate essentially Dirac field. It is defined as psi dagger gamma 0, and sometimes you also write it like psi bar I del slash minus m psi, where del slash is defined as gamma mu del mu. Right. So, this was your Dirac Lagrangian. So, this is the Dirac Lagrangian, and now let us see how we can firstly calculate the conjugate momenta. So, the conjugate momenta will be defined by pi of mu psi, and that will be nothing but del L of del mu psi. Now, what this quantity is going to be? If you look into this Lagrangian, it is straightforward that if you take the derivative with respect to del mu psi, what remains is I psi bar gamma mu, right. So, this is what we are left with. Then we can also define this with respect to the psi bar, the pi mu psi bar, that will be del L by del of del mu psi bar. Now, what that del mu psi bar is, just looking into the Lagrangian, it is clear that there is no term of such, and so this is going to be equal to 0. So, we can also then say that pi of 0 psi, when we put mu equal to 0, this is going to be I psi bar gamma 0, which is nothing but I psi dagger, because psi bar is psi dagger gamma 0 and gamma 0 square is equal to 1. Now, let us construct the Hamiltonian, and once again from the definition that the Hamiltonian is pi 0 psi del 0 psi minus L. Now, I am not going to do this calculation, but this is actually straightforward to carry this calculation to show that this turns out to be psi dagger minus I gamma 0 gamma I del I plus m gamma 0 psi. Okay? So, this is exactly what the Hamiltonian turns out to be. Now, this is simply something that you can do in a couple of steps if you write it explicitly. So, please do check this step. Let us once again get back to the Dirac equation. So, the Dirac equation is essentially the Euler-Lagrange's equation that you derived from the Dirac Lagrangian, and that is simply I gamma mu del mu psi minus m psi is equal to 0. Now, if you split this first term component wise, then you can say that this I gamma 0 del 0 psi is nothing but equal to minus I gamma I del I psi plus m psi, right. So, I have just written gamma mu del mu as gamma 0 del 0 plus gamma I del I. So, therefore, this is what you have. Now, you look into the Hamiltonian once more. So, what you basically have is minus I gamma 0 gamma I del I plus m gamma 0. Now, let us look into this right hand side of this term. So, this is what you have basically minus I gamma I del I psi plus m psi with a gamma 0 which is actually being multiplied from the left. So, therefore, H is psi dagger, gamma 0 you are taking out, and this is minus I gamma dot del plus m, and this quantity from the Dirac equation you can replace from here, right, and this turns out to be what? This turns out to be, you know, गामा 0. सो दिस इज गामा 0 तो था ही, उसके बाद फिर से माइनस आई गामा डॉट डेल प्लस एम इज आई गामा 0 del 0, right. So, this is what you actually obtain. Now, therefore, the gamma 0 square is actually 1. So, this is psi dagger I del 0 psi. This is as simple as that. So, this is exactly what the Hamiltonian looks like. Now, the next step, step 3, that you impose the equal time anti-commutation relation in this particular case. You remember that when we impose the quantization, so this is the so called quantization condition that you now impose field valued operators, right. I mean, these fields have now become operators. I mean, they no more remain the field, and you impose the quantization condition. This is exactly in parallel to the quantization condition that we actually had in quantum mechanics, which is like x comma p equal to I h cross. So, now for the fermionic fields, just because we have to resort to this Pauli's exclusion principle, and we are not allowed to have two fermions in the same state. So, therefore, instead of having the commutation relation, this turns into anti-commutation relation. Now, if this feels a little amusing to you, you go back and check this occupation number representation for both the scalars and fermions, where this story will be more clear. Okay. Now, anti-commutation relation is what? Like if you have the anti-commutation of A comma B, that basically means AB plus BA, where the commutation relation is essentially AB minus BA, and of course, if these are numbers, this AB minus BA will identically go to 0, but just because these are operators, now these are not going to be equal to 0. Similarly, we impose the anti-commutation relation on this fermionic fields, which is like psi a t comma x, psi b dagger t comma y, that will be essentially given by delta cube of x minus y into delta a b. Okay. So, this is this thing, and then you know, so this is the commutation relation between psi and psi dagger. So, psi dagger, if you remember that when we found out this conjugate momenta, that is essentially coming in terms of psi dagger. So, this is field and the conjugate momenta, field and conjugate momenta, that is where exactly the commutation or the anti-commutation relation has to be imposed. So, this is what is there for the Dirac fields or the fermionic fields. On the other hand, all the anti-commutation relations for the fields with themselves, like psi a t x comma psi b t y, or psi a dagger t x comma psi b dagger t y anti-commutation relations, these will actually go to 0. And this has to be sort of now explained, or rather it has to be emphasized that these are possible when you have the mode expansion of the fields with respect to the creation and annihilation operators. And from the experience of that we actually had for the field of defining field phi x, we basically said that this phi x field essentially describes the annihilation of particles and creation of antiparticles. So, similarly for psi x, what we have to do, that we have to talk about creation of anti-fermions and annihilation of fermions, or annihilation of electrons and creation of anti-electrons. So, if we have to do that, how do we do that? First, we have the integral measure dqp by 2 pi whole to the power 3 by 2 into 1 by 2 p whole to the power half, and then it has to be summed over the spins, because we know that we have for each, psi will have 4 solutions. That is what we have seen, that you have US and VS, where S is 1, 2, VS also takes values 1, 2. These are the ways of taking, all the positive energy solutions of the Dirac field, Dirac equation, which we actually have taken into account. So, basically what you have, that you have US accompanied with what you call ASP. So, this is basically the annihilation operator for the fermions. So, this is what stands for annihilation of fermions. On the other hand, you also have, and this describes basically the spinors associated with the particles, and then you have VSP, which is the spinor describing the antiparticles, and this operator BSP dagger, that is going to describe the creation for antiparticles, right? Creation for antiparticles. And of course, this has to be aided with the phase space part, which is e to the power minus IPX here and e to the power IPX for this antiparticle part. And this has to be summed over all the possible spins, and here just because we have explicitly used, so there are basically 2 possibilities, like spin up and spin down, or you can say S equal to 1, 2. So, similarly, I can do the mode expansion for the psi bar. So, this hat, you remember, is to make sure that this is now the field, but the field has become an operator after you have written in terms of creation and annihilation operator. So, once again, what will be psi bar hat? That will be sum over S equal to 1, 2. Instead of US, what shall we have? We shall have US bar P, and then for instead of having ASP, I will have ASP dagger, and instead of e to the power minus IPX, I will have e to the power IP dot x. These are 4 momenta, remember. And similarly, instead of VSP, I have VS bar P here, and BSP dagger के बदले में we will have BSP and e to the power, once again this will be minus IP dot x. Now, what does it represent? It actually represents the creation, because ASP dagger is creation of fermions and BSP is annihilation of antifermions. So, psi bar, if you wish, actually this indicates the creation of particles and annihilation of antiparticles, right? And of course, we must have the anti-commutation relation, which has to be imposed on this creation and annihilation operator itself, which will then culminate into, when you use the mode expansion together with this anti-commutation relations, will culminate to the anti-commutation relations that we have imposed on the fields and their conjugate momenta. Okay, so what this will be? So, ASP anti-commutation with ARP dagger, that will be equal to BSP comma BRQ dagger, that will have basically delta cube of, P and Q are the momentum indices. So, this is delta cube of P minus Q, and of course, I must have delta of S and R. So, that is what we must have. So, this anti-commutation relation, if you use together with the mode expansion, will actually give you the anti-commutation relations that you have defined actually for the fields themselves. Now, what shall we do? That now it's the job of us to write the Hamiltonian. So, the Hamiltonian, as we calculated before, is psi dagger I del 0 psi, which is nothing but psi bar, I del 0 psi. Now, remember, these are all now this field operators, so to say, which we have now expressed in terms of this mode expansions, that we have already defined here. And so, using this mode expansions, I am not going to go through the calculation, but you should do. Okay. So, if you use this expressions and a little bit of algebra, basically you can show that the Hamiltonian turns into a beautiful expression which is like integral of dqp sum over s equal to 1 to 2 EP, okay, with AS dagger ASP, BSP dagger BSP, which is basically the sum. So, this is basically the occupation number, if you want to say, for the particles ASP dagger ASP, where BSP dagger BSP is essentially the number of antiparticles. So, you can say the Hamiltonian nicely describes, sum of energies of the particles and antiparticles. So, now we essentially basically actually get this description of rather a particle like descriptions out of this quantization procedure that we adopt. And of course, given the U1 global symmetry that this Lagrangian possesses, this is something that we discussed before, that you can find that the Noether current is something psi bar gamma mu psi, and so this is, see, there is one point which I must clarify here. So, we derived the Noether's current essentially for the classical fields, right? But the point is, I mean, you can do the same exercise after you impose the quantization condition and after you sort of derive the Lagrangian in terms of those field operators which are now expressed in terms of this creation and annihilation operators, and you can show that this expression for the current essentially remains the same. And similarly, you can correspondingly also derive the Noether's charge, and that will come out to be something like sum over S ASP dagger ASP minus BSP dagger BSP. And this is very interesting because the charges of the electrons and positrons differ, right. So, electrons have -1 charge where the positrons have +1 charge. So, the conserved charge here is essentially the number of electrons minus number of positrons. So, number of particles minus the number of antiparticles, this reflects the charges being swapped for the particles and antiparticles. So, that is an interesting part of the story, but you can also do this calculation explicitly using the quantum, or rather the operator expression of the field values psi and psi bar, which we did. So, but the bottom line is, after whole of this exercise that we have done here, we can basically say that now we are elevated to say that the electron field or the Dirac field that we introduced and wrote that Dirac Lagrangian with now has the interpretation of a particle, and that can describe what you call the electrons. Okay? So, that's excellent. Now, let us go back and see if you can do the same exercise for the photons. So, now we did the field description of electromagnetism, and now my job will be to going through the quantization procedure. I am not going to do the detailed calculation, but I am going to highlight how to do the calculation. I mean, how to do the calculation, but not the details of it. This is something which is part of the quantum field theory course actually. But unless we have this kind of notion in mind that how these fields actually becomes particles, we do not have this association to say, okay, now I write the Lagrangian for this guy. Although if I do not write the explicit explanation of the field operators in terms of the annihilation and creation operators, but we have that in the back of our mind that these are once quantized, they describe actually particles. So, now let us do it for the electromagnetism. So, you remember the Lagrangian that we actually wrote, so which is -1/4 f mu nu f mu nu. Now, I am actually going to write it for the massive electromagnetic fields. So, I have added one mass term like half m square mu mu. Okay. Now, what was the definition of f mu nu? Do you all recall that this is del mu a nu minus del nu a mu. correct, and mu essentially is the vector field, which having Lorentz index, that basically means it's a vector field. It's a vector field means it transforms like a vector under Lorentz transformation. So this is the Lagrangian that you have, and if you now do the find the equation of motion using Euler-Lagrange's equation, then what you get? You basically get del mu F mu nu plus m square nu equal to 0, and this is actually what is called a Proca equation. Now, this is something which I did not check, and you must do it as a homework exercise. Okay? So, do write the Euler-Lagrange's equation. I actually did partly I think in the initial case, and so this is this. Now, let us take another derivative. So, let us write del nu of f mu nu m square del nu nu equal to 0. Now, the point is that del mu f mu nu, that is actually J nu, and that is the conserved current. So, when you take another del nu on top of that, the del nu J nu, this is going to be equal to 0. So, the first term of this is actually going to get vanished. So, this is going to get to 0. So, what does this leave then? This leaves m square del nu nu equal to 0. Now, if you have m square del nu nu equal to 0, you basically say, okay, this is nothing but del nu nu, that must be equal to 0. Okay. So, now let us get back to this term del mu f mu nu. So, del mu f mu nu में क्या है? Del mu of del mu a nu minus del mu a mu. Now, from your definition, because del nu a nu equal to 0, matlab nu is a dummy index, I can replace that nu by mu, alpha, beta, whatever that you want. So, that means the second term del nu a nu mu, this term is going to give you 0. So, therefore, what does it remain? It basically gives that del mu f mu nu, this is nothing but del mu of nu. Del mu with those two mu indices are up and down, that basically means the box operator or the del square operator, which you call D'Alembertian and whatever. So, therefore, this equation del mu f mu nu plus m square nu equal to 0, with del mu f mu nu reducing to del square nu, basically tells you that this is box plus m square nu equal to 0. Now, this equation is also something which is we are something familiar with. So, somehow resembles with E square equal to P square plus m square, right. And this also explains the reason that why in this Lagrangian I actually took a plus sign here for the mass term, because the equation of motion should resemble this E square equal to P square plus m square kind of a term. So, this is the construction of the Lagrangian and then the equation of motion for the electromagnetic field. Now, let us construct the conjugate momenta, and just remember that you already pose a Lorentz index for the field itself. So, therefore, when you construct the conjugate momenta, you basically are going to have something like pi mu nu, right, and that is going to be defined like del L of del mu a nu, right. And once you have the expression of the Lagrangian, which is like minus 1 by 4 etc. f mu nu, you can calculate this derivative to come to del nu a mu minus del mu a nu. Now, this is once again something that you are going to do it explicitly, although this is kind of seems obvious, but this is not quite so, and you have to get habituated with handling these tensorial notations mu, nu, etc., etc. So, pi mu nu is del nu a mu minus del mu a nu. But remember that what we actually required is pi 0 I in order to define the Hamiltonian. Now, pi 0 is actually equal to 0, and pi 0 I is something like del I a 0 minus del 0 a I, and that is nothing but E I, which you can call the electric field essentially, right. Now you can construct the Hamiltonian. So it's time that you can construct the Hamiltonian. How do you define that? This will be pi of 0 I del 0 a I minus the Lagrangian. And now if you write this, then you will find out that this takes an expression which is like half of E square plus B square plus M square A square plus 1 by M square del dot E whole square minus divergence of E into A0. Okay. So this is, so the excepting for this last term which is like a total derivative. So this is what the energy essentially associated with the electromagnetic field. So therefore it looks nice, it looks consistent, the construction of the Hamiltonian. I didn't do the calculation. Once again, please check, please check. अच्छा, यहाँ से वो इलेक्ट्रिक और मैग्नेटिक फील्ड कहाँ से आता है? दैट इज एसेंशियली कमिंग, यू नो, द एसोसिएशन ऑफ, यू नो, योर AI. You remember how we wrote the AI in terms of, you know, gradient of a scalar, etc., etc. So you have the AI describing both E and B fields, right? And that's what the definition that we actually did. Okay, so once we have been able to write the Hamiltonian, now the point will be to impose the equal time commutator relation. Now, just because we have in this whole process what we have done, that we have made this A0 going to 0. So, we do not have A0 into this expression. So, the equal time commutator relation is imposed on AI, that is the field, and you know, you remember that when we tried to compute the conjugate momentum, the pi is essentially the electric field EI, right. So, therefore, I would impose this equal time commutator. Once again, this is a commutator because these are bosons. So, this is AI Tx Ej Ty, and this is going to, the commutator of this is going to be minus I del cube of x minus y g ij, and g ij is going to be equal to minus delta ij for each spatial component. Now, once you have imposed this thing, then you have to basically argue that why these fields are now operators. How is it possible? And that is, the explanation is that once you do a mode expansion of those fields in terms of creation and annihilation operators. But as you remember, the way that we could actually describe the fermionic field with respect to the spinorial. So, the spinorial nature was encapsulated by this US and VS particle and antiparticle spinors. Similarly, for the electromagnetic field, what was actually the component which was carrying this essence that these are vector fields? These were actually what you call the polarization. So, for mu fields or particles, they actually have 3 polarization degrees of freedom, which is described by epsilon mu lambda, with lambda is equal to 1, 2 and 3. So, for example, lambda equal to 0, epsilon mu lambda 0 at m0 you can write simply as 1 0 0 0. So, it has 4 components, each of epsilon has 4 component, but there are 3 kinds of epsilons, right. So, that is basically the statement. Now, it is time that we write the mode expansion. So, the first part is to write first of all the integral measure. So, you remember what will be the integral of dqp by 2 pi whole to the power 3 by 2 into 2 ep whole to the power half. Now, we provided sufficient explanation that how and why exactly that this is the measure which is coming using the Lorentz invariants, right. And then sum over lambda, lambda will be summed over for 1, 2 and 3, correct, or if you wish you can write the 3 above, 1, 2 ऊपर में 3 लिखते हैं. So, this will be essentially now epsilon mu lambda p a p lambda. Now, this a p lambda will essentially denote the annihilation of essentially the photons. So, this is annihilation operator, right, annihilation. and this will be having a phase factor which is missing, which will be like e to the power minus I p dot x. On the other hand, you will also have a term like epsilon mu star lambda p, and that will be aided by a dagger p lambda into e to the power I p x. Note that each polarization has a separate, and this is the creation operator, right. So, this is the creation operator that you essentially have. So, this is the creation operator for, so this is the creation. So, if you have to expand it, you can say that this is okay in terms of, suppose you choose, lambda is equal to 1. So, you have to explicitly sum over lambda equal to 1, 2 and 3. So, for lambda equal to 1, you have this epsilon 0, 1, 1, 1, 2, 1, 3, 1, ap 1 into e to the power minus I p dot x, and then you also have this other term which is like epsilon 0 1 star p, similarly epsilon 1 1 star p, epsilon 2 1 star p, epsilon 3 1 star p associated with ap 1 dagger e to the power I p x, and similarly for lambda equal to 2 and lambda equal to 3, which will give you all this term. And then you impose this condition that you have to have the equal time commutator, or rather the commutator relation between the creation and the annihilation operator, like ap lambda dagger is equal to delta cube of p minus q delta lambda prime, and this is in conjunction with this mode expansion will actually be able to explain the equal time commutator relation that you actually defined here. Now, with this whole exercise, basically you can find, I am not going through this how you can write the possible epsilons, that is something that we are going to take up in the tutorial exercises, but the bottom line is that after the normal mode normal ordering, we are actually going to have a nice particle like look for the Hamiltonian, which is like now dq p e p sum over lambda equal to 1 to 3 ap lambda dagger ap lambda. So, therefore, after you derive this derivation is a little tedious, but I encourage everyone to do that. So, now you are saying that this Hamiltonian that we actually wrote, using the fields upon quantization condition with the mode expansion, and after imposing this equal time commutation relations of the fields and the conjugate momenta, we now really have a nice description of the Hamiltonian, saying that this basically describes a set of photons, so to say. And you can show that for the massive degrees of freedom, for the massive gauge boson, this sum over lambda equal to 1 to 3 epsilon star lambda mu epsilon lambda nu is equal to minus g mu nu plus p nu by p square, whereas for photon, which is for the massless case, it simply actually have two independent polarization, and that is going to give you minus the sum over the polarization, epsilon lambda mu star epsilon lambda nu is going to give you minus g mu nu. So, these are the exercises that you should do at home, but to end the lecture today, we basically confer that upon the canonical quantization, we now have a scalar particle, a fermionic particle, let us call it electron, and we have a vector boson particle, let us call it photon. So, we have essentially the ingredients of quantization, which now allows you to bring out the particle interpretations of all these Lagrangians that we actually have written. Now, we will ask this question, how to bind them together into a setup where the electrons can talk to photon, right. So, that will be the next step that we will do. Okay. With this, let us finish today. Stay tuned, and I am going to see you in the next lecture. Thank you so much.